Hello, so today I'm going to present about our group's presentation for high temperature machinery. Uh, I am Muhammad Hakim bin Shabana. I am the team leader for this group. Here are my team members. So moving on, first we're going to go one by one for the materials. First of all, we have ceramic lining plates. The material analysis. Now, as you can see here on the slide, it is exceptional thermal resistance but inherently brittle. Primary materials, alumina and silica-based compounds. The strengths, extreme hardness, maintains structural integrity at temperatures where metals melt or oxidize. The weakness, brittleness, zero plastic deformation, fails catastrophically under tension and manufacturing flaws. Sintering often leaves micro cracks, which act as stress concentrators. The thermal sensitivity, low thermal conductivity creates steep temperature gradients leading to thermal shock. Next, the failure mechanism for ceramic lining plates. The internal stress and external environment lead to spalling, CTE mismatch, ceramic expansion. As you can see the values right here, steel backing expansion. The result, metal expands faster than ceramic, causing the ceramic to snap or delaminate. So the thermal fatigue, repeated heating or cooling cycles grow microcracks into a crazy network. A high temp degradation, creep, time-dependent deformation, grain growth, a large grains reduce fracture toughness, chemical attack, molten slag, molten slag or metals create eutectic phases that melt the ceramic surfaces. So we have here proposed improvement for ceramic lining plates, material upgrade, use zirconia toughened alumina, ZTA, uses transformation toughening. Zirconia expands to squeeze cracks shut. Silicon carbide, high thermal conductivity, dissipates heat faster, reducing gradients. Design change, segmented plates. Replace large monolithic plates with smaller segments. Use expansion joints to accommodate the metal backing's movement without cracking the ceramic. Processing, hot isostatic pressing, HIP, uses high pressure argon gas during sintering, eliminates internal pores and micro cracks for a near perfect dense product. Now moving on to the next component, the polymer conveyor components material analysis. So here is a diagram of how a polymer is made. We get ethane, and then through polymerization we get polyethylene. So commonly used materials, thermoplastics, nylon, PA6, polypropylene, polyethylene. Right? The advantages in moderate temperature environment, 80 degrees Celsius, 220 degrees Celsius, due to first good toughness, able to absorb impact and vibration while maintaining structural integrity. Second, good wear and abrasion resistance, maintains smooth operation without cause softening. Lightweight, reduces loads on motors and support structures. Low friction surfaces, reduces heat generation during sliding contact. Excellent corrosion and moisture resistance, performs reliably in humid or wet environments. Weakness in high temperature environment over 120 degrees Celsius. High coefficient of thermal expansion, expands significantly in high temperature environment. Low glass transition and softening temperatures, meaning material stiffness drop, causes it to lose dimensional stability. So the failure mechanism for polymer conveyor components. Now, first of all, thermal fatigue. During each heating cycle, the polymer softened, while during cooling cycles, it contracted over time. Under sustained loads, this cyclic thermal exposure results in viscoelastic creep and permanent deformation accumulates. Thermal expansion mismatch. In high temperature operation, polymer expand and contract more than other metal components due to its high CTE and generates internal stresses. This can lead to warping because polymer viscoelastic nature will allow partial stress relaxation through creep. Material degradation. Exposure to heat over time will cause polymer chains undergo chain scission, which reduces molecular weight and disrupt internal structures. For the result, the polymer stiffness and strength will be lower than usual, cause it to form creep easily. Environmental factor. First, oxidation and surface aging due to heat and industrial gas exposure. Second, swell and soften due to moisture absorption. Third, localized heating and wear due to frictional contact. Moving on. So the proposed improvement for polymer conveyor components, material upgrade, change conventional thermoplastic to high temperature polymers such as PEEK or peak. Polyamide have high elevated temperature, 250 degrees Celsius to be exact, high strength and stiffness, or PTFE has high elevated temperature, 200 to 260 degrees Celsius, and extremely low friction coefficient. Design change add thermal insulation such as alumina silica ceramic fiber blanket between hot zones, rotary dryer, and polymer parts to reduce radiant heat transfer. Post-processing, doing annealing process to relieve residual stresses in polymer structure and reduce tendency for deformation during thermal cycling. Moving on, we have the component here, the composite fan blade. So material analysis, carbon fiber reinforced epoxy polymer CFRP PMC IM7 carbon fiber reinforcement toughened epoxy matrix. Epoxy is thermoset polymer. We can see there's a table here, orientation in fiber direction for elastic molecules GPa 158 to 8.3, Poisson's ratio 0.333 to 0.012. Now, anisotropic based on table above, strong along fiber direction. The benefits are lightweight, high strength, high corrosion resistance. Notes, please note, polymer matrix composite is also known as PMC. Now, the failure mechanism. The thermal fatigue, different CTEs between carbon fibers, low CTE, and epoxy matrix, high CTE, cause cyclic stresses at interface leading to microcracking and debonding. Thermal expansion mismatch between plies, interlaminar shear stresses that leads to delamination. High temperature degradation of epoxy matrix. Epoxy softens near TG, it loses stiffness and load transfer capabilities. As it reaches rubbery plateau, epoxy enters rubbery state. Crosslinks prevent chains from sliding. However, at a temperature of 1000 degrees Celsius, epoxy degrades as covalent bond and crosslinks breaks, making it brittle and crack propagates. For additional info, epoxy degrades at a temperature above 450 degrees Celsius. Coefficient of thermal expansion CTE, glass temperature TEG. So for the proposed improvement of composite fan blade, upgrade the material PMC CFRP into CMC or silica carbide. Silica carbide has high strength and stiffness at high temperature above 1000 degrees Celsius and resist oxidation. Design improvement, optimizing orientation and ply stacking sequence, reduce interlaminar stresses, minimizing delamination, applying protective coatings and leading edge shields, reduce erosion, UV damage, and oxidation. Please note, polymer matrix composite PMC, ceramic matrix composite CMC, carbon fiber reinforcement polymer CFRP, silicon carbide, fiber reinforced silicon carbide, SiC here, and ultraviolet UV. On here, and here are our sources for this research. That's it from me. Thank you.